Let us start lecture 24. In the last lecture, we ended with that discussion on plotting water lines. If we go back to our last lecture, we saw two lines. One belongs to lines involving O2 and one involved H2, rather evolution of H2. Now, we see that this is one line, this is second line, third, fourth, and both the lines, all four lines, for example, these two lines are merging because they have the same slope minus 0.0591. Here also they are merging on the same line, this one as well as this one. So, here also slope was minus 0.591 is basically slope, this is also slope. Now, as we have said that these four lines are equally important and these four lines are to be merged with nickel, those three lines what we have drawn as well as the stability regions of those phases. Here what we will do, we will try to merge them. So, this was nickel, this is pH, and we are trying with so we saw that this slope was also minus 0.0591 slope. This is NiO or NiOH whole 2, rather I put it like this because they are basically belonging to the same family. So, H, this is Ni plus plus region and this is Ni, this is 0.25, and if we extend this line, this will be 0.11 volt. This is one set. The another set is reactions involving, this is 0, let us say this is 0, slope was 0.0591. Of course, we have a pH 7 and here the pH is 6.09 when activity of nickel plus plus equal to 1, and there is one more line which has a slope 0.0591 with a minus sign. Of course, we have seen that below this line acidic reactions, those are reactions for the acidic part would happen, and on the right side basic reactions would happen. And then if we club them, so let me draw the water lines. This is 0, let us say this is 0. This region is Ni plus plus, this is Ni, and now before this beyond this and then here also we get this reaction. On the left side this line, H2. Now, we know the regions in nickel system Ni plus plus Ni and NiO or NiOH whole 2, but we have to also see the regions. This is 1.227 volt, this is 0 volt, this is 0 volt. We have to also see that on the right side, for example, if we consider this particular pH, right side of it and left side of it, what are the phases that could be stable or that would be the spontaneity. Similarly, here also if we see the right side and left side, we have to see, for example, if we reach to this position and this position, what are the phases that could be possible. That will be decided by the reaction equilibrium at that point, because this particular diagram also talks about the equilibrium between different phases. So, let us consider, and that is what we once we finalize what are the phases that are possible, then we can also finalize what are the phases that would be existing between this line and this line, as well as what could be possible above this line and below this line, as well as here above this line or below this line. So, in order to do that, we have to see the reactions. First, for example, consider what reactions is possible at this point, which is the equilibrium point. Now, the reaction that is possible is O2 plus 4H plus 4E equal to 2H2O. Now, once it reaches equilibrium, so since I am not changing the potential, I am changing the pH. So, if we are here and if we are here, both the cases the pH values are different. Now, if I consider that oxygen partial pressure remains 1 atmosphere and H2O, definitely it will be always considered to be pure, and then it does not have its activity is considered to be 1. Then depending on OH values, these pH values, I can get different concentration of H plus ion. So, left side pH is less, but OH ion, sorry, this should be H plus ion concentration is more, and here we have pH is more. So, H plus ion concentration is less. So, they are inversely proportional, because there is a minus log of H plus ion concentration is nothing but the pH. So, now at this position, if we have high amount of H plus, in order to maintain equilibrium, the reaction should move this way. So, if we move this way, so left side of this particular point, we will always have H2O. And similarly, on the right side, since pH is more, so H plus ion concentration is less. In order to maintain equilibrium, the reaction should move this way. So, beyond at this point we have oxygen evolution. Okay. So, more amount of oxygen would generate. Similarly, if we consider this, so at this point similarly on the neutral or basic region also, depending on the pH, for example, here we have pH more, H plus ion concentration is less, here pH less, H plus ion concentration is more. Now, here is a problem. The problem is we cannot, though we see that this particular situation holding true, but here when the pH is more than 7, we do not have the existence of H plus ion. So, we have the existence of OH minus ion. So, if we have H plus ion to be less, so OH minus ion concentration would be more. and here H plus ion concentration is more. So, OH minus ion concentration would be less, and when the pH is more than 7, the reaction is H plus 2H2O plus 4 E equal to 4 OH minus. Now, at this point we see that the OH minus ion concentration is less. Sorry, we put a wrong connotation here. So, pH is less, the H plus ion concentration is more. So, we see that this point we have higher OH minus ion concentration compared to this point. So, if we have higher OH minus, the reaction would move this way. So, we will have oxygen generation. And so, the oxygen generation would be always on top of this line, and below that we have H2O. Okay. So, now let us see what happens for the reactions which are not involving oxygen, rather H plus and OH minus. And of course, on the line right side of 7 we have H2O involved. But interestingly, if we consider this point again, just I forgot to mention that we have less amount of OH minus. So, then the reaction should go this way. So, which would increase the pH level of the system. So, that means it will also increase the OH minus ions concentration, trying to increase the OH minus ion concentration. Now, let us come back to these 2 points. Now, here pH is more and pH is less here. So, H plus ion concentration is more and H plus ion concentration is less here. So, now if we consider this reaction, so then at this position, since the H plus ion concentration is more, so the reaction would this way go down the right side. So, gaseous hydrogen would generate below this line. Now, if I consider this point, there H plus ion concentration is less. So, the reaction would try to go this way. So, we have more and more H plus ion concentration, and then it will increase the acidity of the water system. Now, similarly, we can have similar argument here, this and this point we can have pH high, pH is less, H plus ion concentration is more, OH minus concentration is less, and here pH is high, H plus ion concentration is less and OH minus ion concentration is more, because pH and pOH are inversely proportional. So, I can say not pH and pOH, rather H plus ion concentration is inversely proportional to 1 minus . So, this is the relation we have. So, that is what we have this particular correlations. Now, if I take these things in this particular equations, if we consider at this point first, their H plus OH minus concentration is less. So, this concentration is less. So, in order to maintain that concentration, the reaction should go on the right side. So, hydrogen evolution again starts. So, below this line we have hydrogen evolution, and at this point we have H plus OH minus concentration is more. So, this concentration is more. So, the reaction should go this way. So, water we will get water. So, that means below this line we have H2 gas, and above this point, above this line, this water line, we have O2 evolution, and within this zone we have H2O. So, this is the basic mode of constructing this Pourbaix diagram. Now, what is the importance of specifying that which one would be O2 and which one would be, where would we get O2 gas evolution and where would we get hydrogen gas evolution? That would be decided by the potential pH coordinate during polarization. So, we will talk about polarization later on. Polarization, for the time being, let us understand this polarization. Polarization is nothing but the shift in potential from any stable potential. Now, here we are talking about equilibrium. So, it is basically the equilibrium potential. Now, if we somehow, I am here and I am here. Now, at this point my potential pH is this, and at this point my potential pH is this. Now, here once, since the pH I am not changing, so I am changing the potential. Once I go from lower to higher potential, once I cross this particular line, then we would get oxygen evolution, and we do get bubbling when we do experiment during polarization. Polarization means if this is my stable potential, this point is stable potential or the equilibrium potential. If I go to positive side, we call it anodic potential, anodic polarization. If we go to negative side, we get cathodic polarization. So, during cathodic polarization, in this case we get water, and if we do anodic polarization, from the equilibrium polar potential we get oxygen evolution. Similarly, here if you see, this is the equilibrium potential at that pH value, this is the pH value. So, now if we go anodic polarization, that means the polarization is taking place from the positive side, from the on the positive side from the equilibrium potential. So, then we get water, and if we go below that, then we get hydrogen evolution. That is what happened during polarization. So, we will talk about that later on. So, for the time being, that is what we have to make sure, that which region is water line, water, and which region is gas. So, on top of this particular line where it involves oxygen, we have oxygen evolution, and this line which involves H2 evolution. So, below this line we get H2 or the gas evolution, H2 gas evolution. So, the final diagram we have to do it this way. This is pH, this is E, let me do the hydrogen line. This is basically hydrogen line. So, below this line we have hydrogen evolution, and this we call it oxygen line. Above that we have oxygen evolution, and between this, so let me draw it with between this we get H2O, and this zone is NiO, NiOH whole 2, this zone is Ni plus plus, and this one is Ni. So, this is my complete Pourbaix diagram for, or we can say for nickel. So, it is basically indicating H2O system. Fine. So, we have done this is basically the simplified version. In nickel there are other reactions involved, and we can call it as corrosion zone. This is immune, this is passive. Now, let us take one more example. So, here I will not draw the diagrams, I will not do the calculations, I will leave it to you to do the calculations, but there is a small crux here. So, I will discuss that crux here, because whenever we do take equilibrium, we have to club it into two segments. Is basically we have to see those equations, the reactions, and accordingly we will choose, we block them, actually we will segregate them into according to the reaction species that are involved in those reactions. So, best example is aluminum. So, in aluminum system we can have following reactions, and here I am taking one extra species. Then you will understand why I am saying that reactions, after looking at the reactions, you have to block them, you have to segregate them in segments. So, aluminum, these are the reactions you can consider. Then 3Al I am just writing the equations first. And then of course, we have water equations. So, we have written all those equations. Now, you see that this 1, 2, 3, these three equations can be clubbed together, because here we see three products, three spaces rather, 1, 2 and then 3. See this H plus and H2O, we are not considering the species here, because we have to see the metal reactions first, the way we have seen in case of nickel, and then we will talk about water reactions. These three can be clubbed. This is club number 1, and the another clubbing that is possible, if we see 4, 5, the clubbing could be this 2. Now, first 3 we see that aluminum and Al plus 3 and Al2O3 are the reactants or the products that involve aluminum. And in the second set we see aluminum, Al2O3 and AlO2 minus, these three species are involving aluminum. So, second set we do not have Al plus 3 and the first set we do not have AlO2 minus. So, that means the first set whenever we see those phase boundaries or rather stability diagrams, then that will involve only those equilibrium between all three phases like Al3 plus, Al and Al2O3, and the second set would involve equilibrium between Al, Al2O3 and AlO2 minus. And then you can have those data. You already have the water data, then only you need to have mu of Al3 plus equal to minus 481,200 joule per mole, then mu 0 Al2O3 equal to minus 160,8900 joule per mole, and mu 0 AlO2 minus equal to minus 839800 joule per mole, and remember mu 0 Al would be 0. So, once we have data, and then H2O, mu 0 H2O you can find out from previous lectures, mu 0 H plus as well as mu 0 H minus, you can find it out from the previous lectures. Now, if we draw the Pourbaix diagram, you will see that the first three set will have diagram like this. So, here it is Al plus 3 plus Al and Al2O3, and the second set will have diagram you will have this diagram. So, you see that this indicates this line, this one indicates this line, and this one indicates this line. And here this one is nothing but this one is nothing but this, and this one is nothing but this. So, if we club them, you will see that the plot will come here minus, and of course, you will have diagram for these 4 reactions. So, those diagrams, since this will be much below this is a very highly negative, from this value you can find out, you will see this would be hydrogen line, and then oxygen line would be above that, this would be oxygen line. So, this is the complete Pourbaix diagram for aluminum H2O system. Only thing is you need to find out these values from these data and then plot it by doing this clubbing, this 2 clubbing. You should get it. And another important aspect is, here you will see the slope is decided by the number of electrons and number of hydrogen that are participating in the reaction, which involves potential and pH. So, let us stop here. We will continue our discussion in our next lecture. Thank you.